Welcome. You know how to use variables and functions. Now it's time to design your own types. In this lesson, you'll go from raw data scattered across your code to well-encapsulated classes that enforce their own rules and stay valid. We'll cover structs, classes, constructors, the rule of 0, the rule of 5, and modern value types. By the end, you'll have a practical checklist for designing any type cleanly. Let's get started. The simplest way to bundle related data is a struct. Here we define a point with two doubles, x and y, both initialized to 0 with empty braces. Then we create a point with values 3 and 4. A struct groups related values under one name. Instead of passing x and y separately to every function, you pass a point. The type gives meaning to the data. This is the first step toward designing your own types. Identify values that belong together and give them a name. Without classes, related data is scattered across separate variables. Validation is manual and duplicated. There's no single place that defines what a valid state looks like. With classes, data and behavior live together. The constructor enforces invariants, rules that must always be true. The interface exposes only what callers need. This isn't about complexity for its own sake. It's about making invalid states impossible. When a bank account class guarantees that the balance is never negative, every function that receives a bank account can trust that guarantee without rechecking. That's the real value of encapsulation. 4 habits for designing good types. First, bundle data with the functions that operate on it. If a function only makes sense in the context of certain data, it belongs as a member function. Second, enforce invariants in constructors. If a value can't be negative, reject it at construction time. Don't let invalid objects exist. Third, keep interfaces small. Expose only what callers need. Every public member is a promise you have to maintain. Fourth, prefer value semantics by default. Types that copy, compare, and assign like integers are the easiest to reason about. These 4 habits apply to every type you'll ever design. Member functions live next to the data they operate on. Here, we have a rectangle struct with width and height. We add 2 member functions. Area returns width times height, and perimeter returns 2 times the sum of width and height. The const keyword after each function signature means these functions don't modify the rectangle. They only read it. This is important. Const member functions can be called on const references, which means they work naturally with the pass-by-const reference pattern from earlier lessons. Adding behavior to a struct is how you move from raw data to a type with meaning. Now let's build a real class with encapsulation. Bank account has a public constructor that takes an owner string and a balance. The member initializer list, the colon after the parameter list, initializes the private members directly. We use std_move on the string to avoid an unnecessary copy. The class exposes 3 public functions. Deposit adds to the balance, balance returns the current amount, and owner returns the name. The data members are private. No code outside the class can modify them directly. This means the class controls all mutations. If we wanted to add validation, say, preventing negative deposits, we'd add it in one place, the deposit function. That's encapsulation in practice. The only technical difference between struct and class in C++ is the default access level. Struct members are public by default. Class members are private by default. That's it. But the convention carries meaning. Use struct for plain data aggregates, types with no invariants to enforce. A point with public x and y is a struct. Anyone can read or write the values, and that's fine because there are no rules about what combinations are valid. Use class when you need to control access and enforce invariants. A bank account with private balance is a class because you need to ensure the balance is never negative. The rule is simple. If all members can be any value independently, use struct. If the type has rules, use class. The rule of zero says, if your data members manage their own resources, you don't need to write a destructor, copy constructor, copy assignment, move constructor, or move assignment. The compiler generates correct versions automatically. In this student class, the members are a string and a vector. Both manage their own memory, so the compiler-generated copy will copy them correctly. The compiler-generated move will move them efficiently. The compiler-generated destructor will clean them up properly. You write nothing, and it all works. This is the default you should aim for. Design your types so that the rule of zero applies. Use standard library types as members and let the compiler handle the special member functions. Sometimes the rule of zero doesn't apply. When your class directly manages a raw resource like a heap allocation, a file handle, or a network socket. In that case, the rule of 5 applies. If you define any one of the 5 special member functions, you should define or explicitly delete all 5. The 5 are destructor, copy constructor, copy assignment operator, move constructor, and move assignment operator. In this buffer class, we own a raw pointer to allocated memory. The destructor must free it. The copy constructor must allocate new memory and copy the data. The move constructor must transfer ownership without allocating. If you define some but not all, you risk leaks, double deletes, or silent bugs. Define all 5, or better yet, restructure your type so the rule of zero applies instead. C++20 introduced the spaceship operator, formerly called the three-way comparison operator. When you write auto-operator spaceship const point reference const equals default, the compiler generates all 6 comparison operators for you: equals, not equals, less than, greater than, less or equal, and greater or equal. For a point with x and y, it compares member by member in declaration order. This means you can sort points, use them as map keys, and compare them with equals, all without writing any comparison logic yourself. Default comparisons are one of the best features of modern C++ for value types. If your type should be comparable, add the defaulted spaceship operator. 4 rules for writing good constructors. First, use member initializer lists, not assignment in the constructor body. The initializer list, the colon syntax after the parameter list, constructs members directly. Assignment in the body, default constructs first, then assigns, which is wasteful. Second, take strings by value and std move into members. This handles both L-value and R-value callers efficiently with one overload. Third, mark single-argument constructors explicit. This prevents accidental implicit conversions that can cause subtle bugs. Fourth, validate in the constructor. If a balance can't be negative, throw an exception right there. Never let an invalid object exist. These patterns keep your constructors clean, efficient, and safe. Here's a quick design checklist for any type you write. Does this type need invariants? Use a class with private data and public interface. Is it a plain data aggregate with no rules? Use a struct with public members. Do the members manage themselves? Apply the rule of 0. Let the compiler generate the special functions. Does it own a raw resource? Apply the rule of 5. Define or delete all 5 special members. Is it a value type that should be comparable? Add the defaulted spaceship operator. For next topics, continue with OOP and polymorphism to learn how inheritance and virtual functions enable runtime dispatch. Then memory management to learn how smart pointers and RAII handle lifetimes automatically. You now know how to design types. That's a major milestone. Thank you.